So let us discuss this example, okay, of a matrix space. See, D is defined in this way, and it is defined on set of natural numbers. So you are familiar with set of natural numbers. Natural numbers means 1, 2, 3, and so on. Okay, so we have this set, and on this set they have defined this function D in this way. See how they have defined this one. See, D of 2 comma 2. So if both numbers are same, their value is 0. So in this way they have defined D. And see, if you have two distinct numbers 2 comma 3, so 2 and 3 are unequal, that means we have to follow the second definition. Okay, so it will be like this: 1 plus 1 upon 2 plus 3, that means 1 plus 1 by 5, right? So in this way they have defined D. Okay, and we have to prove that it is a metric. Okay, so how to prove that it is a metric? It should satisfy four conditions. Okay, so first condition is it should be greater than or equal to 0. Second condition, equal to 0 if and only if m is equal to n. Here d of nm is should be same as d of mn, right? Symmetry. And the last one is triangle inequality. So let us start to do. See, what will I do? I will start with the first property. See, first property, for if I select any two elements, m comma n belongs to set of natural number. See, these are natural numbers, that means 101%, both of them are greater than 0. Agree with me? Natural, 1 2 3 4 5 6, these are natural numbers, so those are obviously greater than 0. So if you add them, what will happen? That is also we get a greater than 0, that means positive number. If you take reciprocal, no problem. Getting? So reciprocal of any positive number is again positive number. If you add 100%, we have a positive, since 1 is also positive and this number is also positive. So we get this is greater than 0. But have you seen it anywhere? Yes, this is definition of D. So 101%, this is greater than 0 and this is equal to 0. So that means if you consider both cases, therefore you can write D of m comma n greater than or equal to 0. In this case we get greater than 0 and in this case we get 0. So that's why I'm writing greater than or equal to 0, and this is true for mn belongs to set of natural number. So in this way we proved that it is greater than or equal to 0. So the first property is proved here. So make a screenshot of it, and after that we will go for second property. Okay, so let us discuss second property. So in second property, if the function has two distinct definitions, if it has only one definition, then we can directly prove it. Okay, we directly start with left hand side, if and only if and only if and only if, and we get the last one. But see, if the function has two distinct definitions, then we have some different technique to prove the second property. Already in previous videos we have seen. Let us see that thing here. So here I will discuss two cases. The first case is m is equal to n, and the second case is m is not equal to n. Okay, so for I'm taking again two natural numbers. For m comma n belongs to set of natural numbers. So let us discuss the first case. M is equal to n implies if m is equal to n, the definition says its value is 0. So therefore d of xy is equal to 0. Clearly I can mention by definition, right? Okay, so by definition. So let us discuss second case. If m is not equal to n, see what will happen. If m is not equal to n, obviously I should follow the second definition. What is the second definition? This is d of, sorry, here instead of xy I should write d of m comma n. So here also d of m comma n is equal to 1 plus 1 upon m plus n. Right? So m plus m is natural number, n is natural number, so definitely this is a positive part. We are adding positive part in 1, that means again we have a positive number, so it is greater than 0. You are getting? So this is greater than 0, this one is also greater than 0, the sum of these two is also greater than 0. That means what I want to say, simply d of mn is not equal to 0. It's greater than 0, that means 101% it is not equal to 0. That means, see, if n is equal to n, then only we are getting 0, otherwise we are not getting 0. So therefore we can write, we can conclude it. So therefore d of m comma n is equal to 0 if and only if m is equal to n, right? So in this way we proved second property. Make a screenshot of it, and after that we will go for third property. See, in third property also, we have to discuss two cases. Since the definition has two distinct cases, right? They have distinct definitions. So see, my first case, if m is equal to n. So if m is equal to n, what will happen? D of m comma n is equal to 0 by definition, right? And d of n comma m, that is also equal to 0. Since both of them are equal, if you consider mn or if you consider nm, both of them are equal, so the value is 0. So that means what I want to say, d of m comma n is same as d of n comma m, since both of them are 0. So that means third property is proved in this case, right? So let us go for next case. I'm talking about next case now. M is not equal to n. See what will happen if m is not equal to n, d of m comma n. See here, m is not equal to n, that means I should follow the second definition. I cannot go for the first definition. What is the second definition? 1 plus 1 upon m plus n. Tell me, can I write 2 plus 3 as same as 3 plus 2? Yes. So here also m plus n is same as n plus m. So let us do that. So this is 1 plus 1 upon n plus m. So which is equal to, so this is definition of what? D of n comma m. So now since we have n first and m later, so that's why we could write d of n comma n. So therefore from above two cases, what we get from above two cases, here also we are getting d of mn is equal to d of nm. Here also we are getting d of mn is equal to d of nm. So therefore we can write d of mn is same as d of nm, and this is true for any m and n which are natural numbers, right? So in this way we proved third property also. So now simply we have to prove the last property. Make a screenshot of it and after that we will go further. Okay, so let us discuss fourth property. Okay, you remember the fourth property, we call it as triangle inequality. That means d of xz is less than or equal to d of xy plus d of yz. Okay, so here instead of taking xyz, I will take natural number. Normally we take n, m, p. Okay, so we three elements are required here. So I will start with for m, n, p, which are natural numbers, right? See, this inequality we have to prove, but see, when the function has two distinct definitions, okay, listen carefully, when the functions has two distinct definitions, that time we need to discuss few cases, and after discussing all these cases we come to the conclusion. Okay, so this is a method we follow when the function has two or three definitions. So let us start with three examples. Already I have written m and p. See, in previous video already we have seen few cases we have to discuss. So I will consider the first case. We have three elements now. If three of them are equal, okay, so my first case is, what is my case number 1? Case number 1 is m is equal to n is equal to p. See what will happen if m n is equal to p. So tell me, d of mp 0, getting, since all of them are equal, d of mn 0 since they are equal, and I will write here d of np, that is also 0 since these are equal. So therefore I can write d of mp is equal to d of mn plus d of np, right? So here we get equality. So triangle inequality is there, but in this case, okay, in first case we get equality. So let us go for the second case. Case number 2, right? What is case number 2? We will consider m is not equal to n, but n is equal to p. See here, n is equal to p. So therefore d of np is equal to 0, right? Since these two are equal, and equal if you have, its value is 0. And I will mention d of mp is same as d of mn. Agree with me? Since p and n, both of them are same, so here you can easily replace p by n, so you will have equality here. What will I do? This is equal to d of mn plus 0. If you add 0, doesn't matter, since 0 plus anything you will have the same term. So this is equal to, see why I'm adding this one, d of mn plus 0. 0 means what? D of np, right? Since the value of 0, this has value 0, so that's why I could write this. So therefore d of mp is equal to d of mn plus d of np. That means here also, okay, in this second case also we are getting equality, right? Same thing we have got. So let us go for a third case. Can you tell me the third case? What will be the third case? Okay, we have a space here. I'm writing here case number 3. Case number 3. So what was our first case? All of them are equal. What is our second case? Last two are equal. The next case will be first two are equal and the last one will be different. That means m is equal to n, but n is not equal to p. See what will happen? Therefore I can write d of mn is equal to 0, since these two are same, and d of mp is same as d of np, right? Since m and n are equal now, so you can easily replace m by n. This is equal to, right, what I'm going to do, 0 plus d of np. I hope all of you are getting my technique, how to prove this one. So I'm adding simply 0 before it. If you add 0, doesn't matter, we have a equality. But see, 0 is the value of this one. So therefore d of mn plus d of np. Agree with me? So therefore what is our left hand side? D of mp, we get equality again. See, in this case also we get equality, and the same thing we have got. Okay, so let us go for next case, case number 4. Can you tell me the case number 4? What will be the case number 4? In case number 4, see what we have assumed, all of them are equal. Next, last two are equal. Next, first two are equal. Next, now I will consider first and last are equal, middle one is different. That means m and p we have now. So now I am considering m and p are same, but n is different. Okay, see what will happen if m and p are same? Obviously d of mp is it's unequal. D of mp is equal to 0 and d of mn greater than 0, and d of np that is also greater than 0. See, mn, these are two distinct, so that's why its value will be non-zero and will be greater than 0. And in case of np also same thing will happen. See, this is greater than 0. Next one is also greater than 0. So if you add, again we will have greater than 0. So therefore I can write 0 less than d of mn plus d of np, since both of them are greater than 0. So that's why their sum is also greater than 0. But see, 0 we have seen somewhere. Yeah, 0 is the value of this one. So therefore d of mp is less than d of mn plus d of np, right? So mp, yeah, here we get equality, here we get equality, here also we get equality, but in this case we get strictly inequality. You are getting the point? Okay, tell me, have we covered all cases? First, all three are same. Next, last two are same. Next, first two are same. Next, first and last are same. So obviously the last case is all of them are distinct. M is not equal to n, not equal to p. So I will go for the last case, but before that make a screenshot of it, and after that we will go for last case. Okay, so let us discuss the last case. So last case is obviously all of them are distinct. Okay, see what will I do? Then, okay, therefore d of mp, d of mp, these are two, so I should follow the second definition everywhere since none of them are equal. So that's why by second definition 1 plus 1 upon m plus p, right? What is value of d of mn? That is also, I should follow the second definition since none of them are equal, right? And d of np is also 1 plus 1 upon n plus p. Okay, right? So see what will happen clearly. Okay, clearly I can write clearly m plus p is greater than 1. Agree with me? Since these are natural numbers, none of them can be negative, getting? So both of them are greater than or equal to 0. If you add, okay, if you add, at least sum should be 2. So it is greater than 1. So if I take reciprocal, what will happen? 1 upon m plus p less than, if you take reciprocal of 1, you will have 1. I'm going to add, okay, 1. I'm going to add 1 on both sides. So if you add 1 on both sides, 1 plus 1 upon m plus p. If you add 1 here, 1 plus 1, 2. But see, this is definition of D of MP. So implies D of MP we got it is less than 2, equation number 1, right? Now, so now I consider, okay, now I consider D of Mn plus D of Np. See how what will happen? D of Mn, what is this value D of Mn? 1 plus 1 upon M plus N, and D of Np 1 plus 1 upon N plus P. See, 1 plus 1, 2, and these two are some numbers. I don't know what are their values, but definitely this is greater than 2. Equation number 2. Getting? So this number, okay, whatever its value, it is less than 2. The sum, whatever its value, it is greater than 2. So if you combine 1 and 2, so from 1 and 2, if you combine, what can we write? D of MP, right? D of MP is less than 2. Getting? This is less than 2, but 2 is less than this one. So this is less than D of Mn plus D of Np. So in this way we get inequality, strictly inequality we get in this case also. So if you consider all cases, therefore from all above cases, so if you consider all above cases, we come to the conclusion that dmp less than or equal to, I am saying less than or equal to since in some cases we get equality, in some cases we get inequality. So this is true for all m and p belongs to set of natural number. So the fourth condition is also satisfied. So all conditions are satisfied. That's why we can declare D is a metric on n. So I expect that you should write just last sentence there in your notebook. That is, you can declare D is a metric on n, and we will stop. Make a screenshot of it, and after that we will stop. Thank you.